For today, we're going to introduce the topic of atomic structure and periodicity. Periodicity derives directly from the name of the periodic table. The periodic table gets its name because it has periods in it. In other words, things start from one side and they go to the end, and if you go one more past that one, it's an element that has similar properties to these back over here. So you just wrap around and start over again. That's a period. But the atomic structure of the elements determines that periodicity. That's why they're both together in the same chapter. So let me share the PowerPoints. And let's see, that's not the way it happens. Let's try it this way. That's better. There we go. Now I need to, let's see, slideshow. Come on. And from the beginning. There we go. All right, let's clear some of this stuff out over way. And so I can see everything. There we go. All right, chapter 7, and it'll be exam 5, and this is the only chapter that will be covered in this exam. And that's probably a good idea because there's a lot of material here. There we go. Okay. There are indications in nature that elements are different, and in fact, the lion's share of the information we gather about elements in particular, whether it's on the Earth or someplace out in space, outer space, we learn things about these elements through the use of electromagnetic radiation, light. In fact, until we started sending probes to other heavenly bodies, that was our only access to the universe, was through the reception of various wavelengths of light. And we can see that evidence in fireworks, right? The brilliant colors that you get from fireworks are due to the excitation through explosions and heat of the various elements that are contained in the firework. Some colors are more difficult to produce than others, but we won't go into that right now. But that's one indication that elements are different, and they're different in their electronic structure. Here we go. We want to know why we get those colors. You know, why is a common question in the sciences. Why do they occur? Why do different elements, or chemicals for that matter, give us different colors? These various, let's see, I've got them covered up here, so let me move that thing out of the way. Here we go. The various elements give you different colors. Sodium tends to be sort of an orangish color. Calcium is more yellowish. Potassium is kind of a reddish pink. Barium blue, zinc yellow. There are others. Strontium I used to use in my lab demonstrations when we had school tours would come through our lab, and I'd do demonstrations for them and use flame tests, show them that different elements produce different colors. Anyway, why do they differ in the colors that they produce? Sometimes an element will give you one color in a flame but a different color when you put it in solution, right? It'd be interesting to know why that occurs. I mean, it's the same element. Why would it give you different colors? Why do some elements produce very similar colors? That's another. I mean, one question is, why do they produce different colors? And then why do some of them produce almost the same color? For instance, we know that iron, when it rusts, produces kind of a reddish color. And iron in the hemoglobin, in our red blood cells, also turns red, but it only turns red when you add oxygen to it. And so there are different effects there. Is the iron in your blood closely related to rust, or is it something different? Oxygen's involved in both cases. So maybe the oxygen does have something to do with that color change, the color similarities. I did my master's research on crawfish and the processing waste that is generated by a company that produces only crawfish tails. They peel the crawfish by hand, put the tails in a bag and freeze them, and send them all over the world. But the exoskeleton of the crawfish, especially after it's been cooked, some before, but definitely after, produces a bright red color. And I did my research on that. And this is the molecule that produces that color. Notice that it doesn't have any metals in it. There are no metals in this compound. It's only carbon, hydrogen, and oxygen. So why would it produce a red color when iron also produces a red color? There must be something in common there. Okay, the key to all this is to focus on the light itself and characterize electromagnetic radiation. We're going to do that first and then relate that, the knowledge of electromagnetic radiation, to the structure of the atom itself. Okay, so we'll do this one first. Electromagnetic radiation, or light, is energy, but it's energy of a specific type, and it can be characterized. In fact, there was discussion for decades, even centuries, about the nature of light. You know, one of the main questions was, does light need a medium to propagate? You know, sound does. Sound transfers energy, but sound will not move through a vacuum. Sound only moves through a medium that has matter in it. But light can, it's like it carries its own medium. Light can travel through a vacuum. In fact, it moves at maximum speed through a vacuum. If it travels through anything else, it tends to slow it down. But we can characterize light with these three terms: wavelength, frequency, and speed, or velocity. So let's characterize them. Right? Wavelength is designated by small Greek letter lambda, like this. That stands for wavelength. What is wavelength? Well, you have to visualize a beam of light as a wave. So it would be like this. And in mathematical terms, that's a sine wave. The wavelength is the distance between two peaks or two troughs. So this distance here is the wavelength. And the international standard, of course, is the meter. So the wavelength would be in meters. That's the standard. But for convenience, we use other types of measurements, and we'll talk about those as we go along. That's the wavelength. That same wavelength, though, that same wave is moving. So another way to characterize it is, if you fix your gaze right here, that's supposed to be an eyeball. If you fix your gaze right there, start your clock, start your watch, and let it run for a second. And count how many of these peaks pass your eyeball. That will be frequency. And frequency is designated by the Greek letter nu, N-U in English. It looks sort of like a V. And that's the number of cycles that occur per second. Okay, now what else can we say about it? Well, we can say that light travels at a certain speed. Right? In a vacuum, we know that it will travel 2.9979 times 10 to the 8th meters in 1 second. So you just have to say, all right, you need some way to measure the time it takes to go a certain distance. And there have been several attempts over the years to quantify that value. And many of them have been very successful. In fact, they all agree with one another. Different methods give you the same value. Okay, so another way of looking at it is, if you start with this peak, how far can it go in 1 second? Not how many peaks can go by your eye in 1 second, but how far can that one peak go in 1 second? And it's about 3 times 10 to the 8th meters in 1 second. That peak there will go that far. All three of these terms, these measurements, are related to one another. And they're related by that formula. We use C as a term, a small c, as the variable. Actually, it's not variable, it's a constant. As the constant term for the speed of light. And that's equal to the wavelength times the frequency. Okay? Now let's just do a quick check to see, so that some smart mathematician doesn't pull the wool over your eyes. What are the units of measure for speed? Meters per second, correct? How about wavelength? What's the measurement for wavelength? Meters. And what's the unit of measure for frequency? Well, it's cycles per second, but cycle is not a measurement. Right? Cycles is, because it's variable, right? One cycle for one light beam can be different from the other one. So the only standard measure for frequency is seconds. It's reciprocal seconds. Right? Cycles per second. When you say per, that means it's in the denominator. So if we multiply that times that, we get this. So our units of measure are correct. And in order for this to work, wavelength has to be in meters. Frequency has to be in reciprocal seconds. In fact, there's another unit of measure that's been accepted. It's called the hertz. And the hertz is just another way of saying cycles per second, right? They wanted to honor a scientist by the name of Hertz for his work, so they gave that measure. Okay. So this shows you the relationship and you can see it from the mathematical formula too. If this is a constant right here, then as this one goes up, that one has to go down. That one has to get smaller as this one gets bigger, or this one gets smaller as that one gets bigger, right? If a product of two variables equals a constant, then the relationship between the variables is inverse. It's like Boyle's law. Pressure times volume equals a constant. That's an inverse relationship. Same thing for this formula. And this is just a picture and trying to get that point across. Right? In 1 second, this 4 Hertz signal can pack in there about 1, 2, 3, 4. Right? 4 Hertz signal means there are 4 peaks in 1 second. What's the distance between those? Well, this is a distance. If we increase the frequency, that is, put more peaks into that same second, then look, the wavelength has to decrease. So there's your inverse relationship. All right, let's talk about the electromagnetic spectrum. Light comes in a very wide range of wavelengths, consequently, a wide range of frequencies. But there's only a very small sliver of this whole spectrum of wavelengths that our eyes can detect. That's the visible spectrum right here. And it occurs between about 4 and 7 times 10 to the minus 7th meters in wavelength. Now, as the wavelength gets shorter, you tend toward the blue. And as the wavelength gets longer, you tend toward the red. So what does that mean in terms of frequency? Right? This wavelength is shorter than the red wavelength. Right? So it's decreasing. That means the frequency must increase. So a higher frequency will be down on this end, and a smaller frequency will be on the red end. Okay, so we get our minds wrapped around the relationship here. The wavelength is increasing from left to right and in meters. And on the red end, you're increasing in wavelength, and you come to infrared, which is a longer wavelength. Then you move to microwaves, like microwave communication or microwave oven. We're talking about those wavelengths. And then we move to even longer wavelengths, to where the wavelengths can be several meters long. And then we're getting into radio waves. And you have a subdivision of those spectra there. FM radio is in the shorter wavelength side, AM radio is on the longer wavelength, and short waves in the middle. Okay, if we go the other direction, below the blue light that we can see is the ultraviolet that we can't see. That doesn't mean it isn't there. And you know the damage it can do. If you stay out in the sun too long in the summer, you find out what ultraviolet radiation can do to your skin. But now the wavelength is getting shorter. So we go through ultraviolet, various types of ultraviolet, and then we get to X-rays, which are much shorter wavelength, and you'll see those in your dentist's office, for instance. they'll bombard your face with X-rays so they can get a picture of your teeth. Or if you break a bone or something, you're going to get an X-ray to find out where the break is. And then even shorter and shorter wavelengths. Notice that we're down to picometers, 10 to the minus 12. Gamma rays. Those are the most energetic light waves in the universe. You've heard of gamma ray bursts. Maybe you haven't. And it's a good thing if the gamma ray burst never finds Earth, because the gamma ray burst from outer space is energetic enough to completely ionize the Earth's atmosphere. It would kill everything, just like that. Fortunately, they're not too common, and they're very directional. They go off in one direction, and that's the only direction they go. So most of the gamma ray bursts that we see are kind of, you would think that if you can see one, that it's aimed at you, but really what's happening is you're only seeing the spread. As light propagates, it tends to spread. So you're seeing just a very small amount of it. And you can tell from other indicators, astronomical indicators, that a gamma ray burst is occurring. That's another topic. So that's the electromagnetic spectrum. And the light itself carries with it energy. And they're related to one another. In other words, you can relate the frequency of light to the energy that the light carries. You can produce light if you pass electricity through it, right? Before compact fluorescent bulbs and LEDs, we used to produce light in light bulbs by, we called them incandescent. That is, you pass electricity through a resistor and you get enough current going through it that it heats it up. And then that little filament in the bulb gives off light. Not very efficient. In fact, they get very hot and they only give off a certain amount of light. But most of it is dissipated as heat. But this pickle is being subjected to a current of electricity, and it's starting to glow. So recall the relationship, the conservation of energy. That is, energy can neither be destroyed or created. It can only be transformed. So that's what's happening here. The energy that's in the electricity is being converted into heat and light in that pickle. Okay. I won't spend a lot of time on this. This is just a historical perspective. James Clerk Maxwell was a mathematician dabbling in physics. And he was able to characterize electromagnetic radiation with a series of equations which treated light as a wave, just like we drew here. That's the way he saw it. And his formulas worked. They were able to predict certain characteristics of light, wavelength, energy, so forth and so on. So his work was considered valid. And to a certain extent, they agree with general relativity and quantum mechanics. So when you see those two terms together, just think general relativity is very big in the universe. When you talk about big things like planets, stars, black holes, general relativity. When you talk about things that are very, very small, then you're talking about quantum mechanics. As it turns out, Maxwell's equations agree with both of them, up to a point. But we don't have time to discuss where that point is right now. And at the beginning of the 20th century, scientists believed that the universe was pretty well explained. So with Maxwell's equations and some of the other work that had been done up to that point, scientists were pretty sure that they understood how the universe worked. Unfortunately, they were wrong. And then we needed to modify theories to include general relativity and quantum mechanics to cover those areas where existing theories didn't work anymore. All right, so there's at least from the beginning of the 20th century, there was a brewing controversy over the nature of light. One school of thought said it's like a wave, like sound waves, like light's a wave. And the equations of Maxwell tended to support that. But there were certain things, phenomena that were observed involving light, which waves could not explain. And the only way to explain them was to treat light as if it were a particle, like a packet of matter. But it's not matter, it's energy. But it had to be treated as if it were a particle of something. So you have these two schools, wave versus particle. And they went back and forth over the decades. And eventually they decided, well, you know, under certain circumstances, light behaves like a particle, and in some circumstances behaves like a wave. It's both, right? So it depends on the problem that you're trying to solve. So this fellow right here, Max Planck, was studying the phenomenon of black body radiation. What does that mean? It's kind of like a big pickle, and it radiates light based on its temperature. How hot is it? Right? So it's a black body to start with. It gives off no light, and it only gives off light when you heat it up. And that's the way we treat our astronomical observations, particularly of stars. When we see a star that tends to be toward the blue, our instruments are calibrated to say that star is very hot. If it's toward the red, then we're saying that star is relatively cool compared to the blues. Right? That's black body radiation. We can quantify that radiation and the energy that is contained in a packet or a quantum of light. And Max Planck did it. And what he said was, the energy that's contained in joules is equal to a constant, which is Planck's constant in his honor, times the frequency of the light. So notice, as the frequency gets higher, the amount of energy it carries gets higher. And the proportionality constant is that value right there. Now, you don't have to memorize it. It's in useful information at the end of the review document. This is how light behaves as a packet of energy, a quantum, a particle. Suppose you don't know frequency. Suppose you know wavelength. Well, we already know the relationship there, right? C equals lambda times frequency, right? So if you know the wavelength, then all you have to do is solve for the frequency and plug that in right there. And that's where this formula comes from, right here. There's Planck's constant, right? It's kind of funny looking, but it does the job. And if you multiply this times frequency, frequency is cycles per second, so the seconds cancel and leave you with joules. And that's how much energy is contained in a quantum of light of a given frequency. All right, this is not going to work. I hadn't had a chance to fix these sets of slides. This is in I can't even remember. It's an Adobe product that they've just discontinued, so these things don't work anymore. Flash, yeah. This is based on the Flash protocol, so I have to skip it. So another thing, besides black body radiation, another thing that was observed was the photoelectric effect. Years ago, decades ago, not too many people had even heard that term, photoelectric effect. But now that we have solar panels everywhere, I mean, the photoelectric effect is part of our daily life. The photoelectric effect takes advantage, the solar panels take advantage of the photoelectric effect. As light strikes the panel, there's enough energy to eject an electron from the surface of the wafer in that panel. And then once it's ejected, it's picked up into the circuitry of the panel and becomes a current and is delivered to whatever, you could have a calculator that works off of a little photovoltaic cell, or you could have a huge panel on the top of your house supplementing your energy usage. Same effect, the photoelectric effect. The reason, well, it has everything to do with this particulate characteristic of light, because one quantum that we also call a photon, like Star Trek photon torpedoes, the photon is the quantum of the packet of light, and it has a certain amount of energy. So when that packet strikes the surface, it has to have enough energy to eject an electron. If its energy is less than required, the work function, they call it, of the electron being released, if it's less than that, nothing happens. If it exceeds that, then you eject the electron, and the extra energy that's left over is used to accelerate the electron, whatever's left over. Okay. So this threshold frequency, which is related to that work function, is required. Any frequency that's greater than that will do the job for any given metal. And it was first observed, photoelectric effect was first observed in metals. Now we can access that effect using silicon and semiconductors. No electrons are emitted, no matter how intense the light is, right? You can have the same wavelength of light coming from a lamp, and then you crank up the current and make the lamp brighter, but it's the same wavelength, the same frequency. So it doesn't matter how bright the light is, if it doesn't have the energy of the one photon based on its frequency, then you won't get any electrons. Okay. Let's see. So, based on observations of the photoelectric effect, the only conclusion that could be drawn and explained was that electromagnetic radiation had to arrive at the surface of the metal in packets or photons. So you can see one side likes waves and one side likes photons. It depends on the physical phenomenon you're discussing. Okay. Now, what can happen with light that's has less energy in its photon? It won't eject an electron, but what it does is it heats up the metal, right? The energy can be absorbed by the surface of the metal, and it just gets hot, but it doesn't eject any electrons. So that's why they're called thermal photons. And that's why your French fries are sitting under a lamp at the restaurant, or your food is sitting under a lamp that looks like it's red. It's emitting infrared light, right? It's not enough energy to damage the food, right? Eject electrons and start causing chemical reactions. But it is enough energy at that longer wavelength, lesser frequency. The infrared light is enough to provide thermal photons, and it just heats your food up that way. Okay. So what does that photoelectric effect tell us about the structure of the atom? The interaction of light and an atom occurs at the level of the electron. In other words, and if you think about it, you've got a nucleus here, and you've got electrons out here, away from the, well, it might have some neutrons too, out here away from the atom. Who's going to see the light first? The nucleus or the electrons? The electrons. The electrons are going to see the light first. They respond to the light. So that's the interaction you get, and that's why you get various colors. Well, that's the beginning of understanding for why you get colors from fireworks or from flame tests. Okay, so it's important to understand that everything happens in this structure of an atom in discrete amounts of energy. In other words, when you have some light here, stands for energy, when you have light interacting with electrons, those electrons are not going to move. They're not going to migrate to a higher energy level unless that light is the exact correct frequency. Anything less, anything greater, they ignore it. So the transition from one level to the next is key. That transition requires energy. And if you go from this level to that level, you need a certain amount of energy based on the wavelength of that light or the frequency of the light. Okay. So that's how electrons interact with light in discrete jumps, discrete packets. Okay. One other thing that we can say is that if electrons can be accelerated to higher and higher velocities with more energy, then we know from this equation that they're moving faster. And that means that they behave as if they have mass. So electrons are particles. Photons can be treated as if they have mass too, because they're transferring the energy that they have to the electron. So photons may be considered as possessing mass. And in fact, Einstein is going to show us in a few minutes that all the matter in the universe is interchangeable with energy, right? E equals mc squared. So all the energy, if all the energy in the universe were converted into mass, of course, it would shrink into something very small. But vice versa, you convert, say, the mass of this marker into energy, you get something on the order, enough energy to probably destroy Beckley. Okay, so there's Albert Einstein. And you know, I'm eating up too much time. Einstein's theory of special relativity proved mathematically that light has mass. Right? Not rest mass, not sitting still mass, but relativistic mass, that is mass of very high velocity. When we say relativistic mass, we mean whatever's moving is moving very close to the speed of light. That's what they mean there. So this formula relates the amount of energy contained in that amount of mass, and the conversion factor is the square of the speed of light. This was confirmed. This formula was confirmed by Arthur Compton in 1922, experimentally. Physics is funny. It's got two groups of scientists. Those are the theoretical physicists and the experimental physicists. And they feed off one another. Right? Sometimes the theoreticals come up with something and the experimentalists try to disprove it. Or the experimentalists just make a discovery, and then the theoreticians have to explain why it happens. Okay, both are correct. Wave nature, particulate nature, we just have to deal with it. Like I said before, nature just does what it does. And it's up to us to try to figure out how to explain it. So here's more evidence that light behaves as a wave. It's called diffraction. And all that's required is for light to impact a surface and find an edge somewhere, right? So you got an edge right here, and you got an edge on that other side. So you got two edges here that make a slit. And this slit serves as a point source for a new wave. And that's what's happening here. This wave hits that and forms a wave that propagates from that out in, it's like waves on a pond. When you throw a rock in a pond, if the water's still, you can see the waves propagating out in a circle. That phenomenon supports the wave nature of light. Another wave function of light is refraction. When light passes through from one medium to another, it changes its speed. And if the medium is transparent and you form it properly, then you can cause the light to bend in desired directions. So that's what my glasses do. They take light and they bend it slightly so that my eyes don't have to work as hard to focus. Okay. Now, there's more information, more experimental information that tells us how light interacts with these electrons. And the difference is between a continuous spectrum, right? If you've ever used a prism and sunlight shine through your prism and form a rainbow on the ground, it's continuous, right? From one side, from the blue side to the red side. But if you take an element and isolate it in a device and excite it so that it gives off light, and then you run that through your spectrum, what you will get is, right, as your wavelength increases, you get discrete lines at specific wavelengths characteristic of that element and that element only. Now that's the clue that leads to the, this leads eventually to the theory that what's happening is these lines are being generated by electron movement from one energy level to another. And since that occurs in only discrete packets, that movement, then the light comes out at a given wavelength and only that wavelength. And that's called a line spectrum. And it's evidence for the quantum nature of electron movement in energy levels around the atom. Okay, so this one's not going to show either. But there's your continuous spectrum. This light bulb is designed to give you a continuous spectrum, which means that there's lots of electron transitions in there to produce all of these wavelengths. But if you just put one element in there, like hydrogen, you'll get these discrete lines, like 4 lines in the visible part of the spectrum for hydrogen. Now we have to explain why that happens. Oh, it's said that the energy of the electron in the hydrogen atom, and for any atom for that matter, any element, the energy of the electron is quantized. That is, it only occurs in discrete amounts, packets. So, let's look at the other way. If for that hydrogen, if the movement of electrons and the amount of energy that is given off by electron transitions were not quantized, then every element would give off a continuous spectrum. If you had infinite variability in the electron movement, then you could have infinite variability in the light that is emitted. So that's why we are able to say that those movements are quantized. Okay. Now we come to Niels Bohr. He was a Danish physicist, chemist. All right. Niels Bohr, and he produced a model of the atom. And he actually, he got his ideas from the solar system, thinking of the sun as the nucleus and the planets as the electrons. And he proposed this model. It seems awful simple now, or simplistic now, but it worked in very limited cases. So he proposed his model for the hydrogen atom. Right? He kept it very simple. He says, this is the way it works for the hydrogen atom. As things get more complex with bigger atoms, then things tend to fall apart. But for now, that's a starting point. Bohr's model said the proton is in the center, right? And of course, we know by this time we already knew of the nuclear atom, so we knew where the protons were. They're in the nucleus, right? And you may have some neutrons in there too for other atoms, but we're going to stick to the hydrogen atom with only a proton. And out here you've got an electron. okay? And it orbits around that proton, just like planets do. If some way you can provide energy to that electron, it will jump to a higher level. Right? So if energy comes in, and it's just the right amount of energy, then it will jump from here to here. If it's a different amount of energy, say more energy, it may jump from there to there. Or it may jump, if it happens to be here, after its first jump, but you provide a little more energy with a different wavelength of light, then it may jump out here. Okay. So what Bohr is saying that is that this is the ground state of that atom, and this is the principal quantum number. 1, 2, 3, 4. Right? I'll come back to that later. That's the ground state. And you can move between these levels. You can absorb light and go up in energy, right? Away from the nucleus is higher energy. Or if you're at higher energy and the electron moves back to a lower energy, it will give off that same wavelength that put it up there in the first place. Notice that the first energy, the gap between the first and the second, is very high. And then the gaps become smaller and smaller and smaller. So the larger the gap, the larger the jump, the higher the energy of the light. Okay? And if the energy is higher, that means higher frequency or shorter wavelengths. So a jump from one of these down to 1 would give you not blue light, it would probably give you ultraviolet light, which we didn't show in that former slide, right? So the visible jumps are between these narrower places, but they're not the only ones, right? You can get ultraviolet jumps, you can get infrared jumps, you can even get X-ray jumps. Right. We're only showing 3 emission lines here, and before we showed 4, correct? 4 lines in that visible range. So here we're only showing 3. And here we're only showing 3. So this would be an orbital diagram of the Bohr model of the atom. So the 4th line is violet, and it's actually a jump from 6 to 2. Right? So they're not showing the nucleus in this one. That is actually the first orbital right there. Nucleus too small. So that's 1. This is 2 right here, where these guys are jumping to. If you jump from 6 to 2, well, we're not showing 6 here, but if you jump from 6 to 2, that's the 4th wavelength that we're missing. Now, the useful part of Bohr's model is that you can actually calculate the energy of an electron jump. Let's see, have I missed somebody? Somebody just disappeared. Okay, I've still got 3. That was the 4th one. All right. You can calculate the energy of the electron for an energy level. And then the difference of the energy at this level and that level is the energy of the light that would be required to make the jump, or the energy that would be emitted when you jump the other direction. And this is the Bohr's formula. This is his constant right here. And this is the little n is that number, 1, 2, 3. The Z number is the number of protons. Right? So for hydrogen, the Z will always be 1. Correct? Remember our diagram of an element? This is A, this is Z, right? The atomic number is Z. Okay. The energy in joules is relative not to the nucleus, but it's relative to infinity. If you eject that electron from the proton, that's infinity. And that's 0 energy relative to the atom. I know it seems counterintuitive, it's the other way around. But that's 0, and then anything from here down is referenced to that. So if n equals infinity, right, then E equals 0. So what does that mean? That means that any calculation here is going to be a negative number, because you're going from 0 to a lower energy, which is a negative move. That's why this term here has a negative in front of it, to make the energy negative. And that stands to reason. I mean, when we talked about thermochemistry, everything was relative to the system. So if you add energy to the system, it's positive. If you remove energy from the system, it's negative. So when the electron comes in from infinity down here, what happens? You lose energy. You go from here to here, and it gives off energy. So that stands to reason that the energy would be a negative term if you jump from a higher to a lower level. Okay, so when only one electron, one proton is present, Z is 1, and this is the formula that you would use for the hydrogen atom. Okay. Let me check my time here. I've only got 45 minutes left. I know I'm not going to make it. What I may have to do, since I have to leave on time, what I may have to do is stop the video recording right at 3:45, and then come back later and finish the video. So then you'll have access to all that information, but it'll be in the form of a video, because I can't do it for you live and make the appointment that I have. Okay. So if the electron moves from one position to another, right? This is similar to thermochemistry, where the delta T, the delta change in temperature, is final minus initial. So in this case, final energy of the electron minus the initial energy of the electron gives you the change in energy. Okay, so final comes first, subtract the initial, and you get the change. If the change in energy happens to be positive, that means you had to add energy and the electron is moving from a lower to a higher level. If the delta E is negative, then that means the electron's coming from a higher level to a lower level, and it doesn't have to be infinity. It can be from a higher n down to a lower n. Then the delta E is going to be negative, because it's giving off energy. Right? And we can simplify this equation. We can factor out this constant value. There it is there, there it is there, factor it out. And then all you have in here is, for the hydrogen atom, it'd be 1, the reciprocal of n squared, minus the reciprocal of n squared initial, final minus initial. There you go. That's what you would use for hydrogen. And in fact, this is the only one that works really well. When Z gets larger, then the deviation from the actual observed energy is different, and it gets more significant as Z gets bigger. Okay, so let's say for hydrogen, you have a transition from 5 to 2. What does that mean? It's coming from a high level to a low level, so it's going to give up energy. And the wavelength is 434 nanometers. All right, what's a nanometer? Nano is 10 to the minus 9th, right? 10 to the minus 9th meters. 434 times 10 to the minus 9th meters. You need to know that because we need to calculate the energy, right? So if the change in energy is this, and we stick in values here, right? Final is what? 2, not 5. 2 is the final one. Initial is 5. Okay. Then you calculate that many joules is part of this transition. That's the change in energy. Then we take the wavelength and we use Planck's equation and calculate the energy of that light. Right? So here it is. Remember, E equals Planck's constant times speed of light divided by wavelength. So we plug all those values in, do the calculation, and you get the energy of the light that's emitted when that electron jumps from here to here. And there's agreement. Okay. All right, so Bohr's model was a very simple first attempt at explaining the structure of the atom. We already knew that the nucleus contained the protons and neutrons, and the electrons were out here somewhere. But Rutherford didn't say anything about what they do when they're out there, just they're there. It wasn't until Bohr and his successors that we started to understand the structure of this electron region. Now this is true. The Bohr model only works perfectly for the hydrogen atom. For everything else, it tends to deviate significantly. And from one way of thinking, that makes sense, because when you've got more than one electron out here, they're interacting, right? They're both negative, so they're repelling one another, and they change the electronic structure and the energy levels around this atom. If you get more than one of them, so you have helium, so you have 2 protons and 2 electrons. Now the electrons are starting to interact, and they're messing with Bohr's formula. Okay. So we can do the calculation for each one of these, right, if we had time. And we're going from 6 to 2, 5 to 2, 4 to 2, 3 to 2. So let's just say, qualitatively speaking, which one is going to be on the violet end? In other words, the highest energy. The violet end would be the shortest wavelength. The highest frequency would be the largest transition from 6 to 2, right? So that one's going to be the violet wavelength. The next one's going to be blue. It's just a little shorter jump even still. It's going to be green, and then orange, red will be the last one. It's just a tiny jump from 3 to 2. So it's valuable to develop an intuition for which one's higher energy. The blue end is higher energy than the red end. Consequently, ultraviolet, X-ray, gamma ray, higher and higher and higher energy as the wavelength gets shorter and the frequency gets bigger. Okay. I'm not going to say a whole lot about this one. We have maybe 1 or 2 problems that are in the review document that talk about this in more detail, and we'll cover those in the review. But there was a scientist named Heisenberg, and it was noticed that they were having difficulty assigning both where small things are located and how fast are they moving. In which case, and actually this is another way of saying it, the momentum, mass times, that right there is velocity. That's not frequency, sorry. Mass times velocity is momentum. So what Heisenberg said was, you cannot know both of them at the same time, especially with very small particles like electrons or even atoms. You can know where they are, but you can't say anything about their velocity. If you are able to peg their velocity to a specific value, then you can't say where they are. This becomes more and more a problem as you get smaller and smaller and smaller. So something like something the size of the human body, yeah, we can know both the velocity and the position, because these two terms together exceed that value for something that's big, right? Simply because that term right there, mass, is huge compared to this value. So for large objects, the Heisenberg uncertainty principle is still there. It's not very, it doesn't have an impact on locating where I am and my speed at the same time. But for very small particles, that becomes a significant uncertainty. All right. So the long and the short of that uncertainty is that we cannot actually describe electrons moving around the atom in circular orbits. We have to refer to them in terms of probabilities. Where is it most likely to find electrons around an atom? And that's what this psi function is. It looks like Trident's pitchfork. That's the Greek letter psi, P-S-I. That function, used in the proper formula, gives you an estimate of where the electron region is at a given energy. Right? So at this level, it's going to be somewhere in here. This level, it's going to be maybe out here a little bit. But they're not circular orbits. Okay, I'm just going to breeze through this one. It doesn't mean a whole lot right now because we haven't talked about what those terms mean. It's just that the probability function gives you an idea of where things are, right? This fuzzy dot up here says it's most likely right there, but it could be out here somewhere. That's what probability means. Another way of describing it is this. You're not going to find the probability of an electron right at the nucleus. That's what this term would be right here. You know, you're going to move out a certain distance before you get a high probability of finding the electron in that region. And then it tails off. That's what that graph means. Okay. So, can we say anything about the size of the orbital? When the Bohr atom did say, right, the energy level 1 is right here. Energy level 2 is right there. Energy level 3 is out there. It was claiming to know exactly where the electron is. But Heisenberg proved that you can't know that. So can we say anything about the orbital size? Well, in general terms, right, this wave function gives us an idea of the three-dimensional distribution, or what we call a density map. The higher the density of the map, the more likely you are to find the electron in that location. Right? So For the hydrogen atom, this orbital we call the 1s, and I'll explain that again in a little bit. The hydrogen 1s orbital is a region of space around the atom where we're pretty sure there's a 90% chance of finding the electron there. Now, there are a series of numbers. Now we're getting into quantum mechanics. And quantum mechanics is all about probabilities. Most likely to find an electron here based on the numbers that we assign to it. And those quantum numbers actually fit into formulas, into equations. And when you put those numbers into the equation, they spit out a probability, a psi function, for where you're going to find the electrons. Now, it's not always spherical. It could be a different shape. And we're going to talk about that in 2 seconds. So these quantum numbers, and there are 4 of them. The first one we've already talked about. That's the principal quantum number, n. And that number starts at 1 and goes on up in single jumps, 1, 2, 3, 4, on up. And what it basically describes is the size of the orbital and the energy. The size means how far is it from the nucleus, which relates directly to energy. So that's what n says. So any electron that has an n number, the same as another electron, their energies will be very similar. They may not be exact because there are other factors involved, but they'll be very, very close to one another. The second number that comes along is the angular momentum quantum number. This number, which is designated L, designated L, is used to define the shape of the orbital. Is the orbital more or less spherical, generally speaking, right? Because this is probability. Or is it some other shape, right? It could be spherical, right? That's my representation of a spherical one. Or it could be maybe dumbbell, or it could be like that, or like that. Or it could be donut shaped. Right? So that describes the shape of the orbital, angular momentum quantum number, L. Now, how do we tell L's? These are like nested numbers. This is the big nest, and this is a subset, and the next one's going to be a subset of that one, and the next one will be a subset of that one. So these numbers are either 1, 2, 3, or 4, on up. The L's are derived from one of these, not from all of them, just one of them. If you have an n equals 2, then L is based upon that 2 only. And it's based upon, it goes from 0 in jumps up to whatever that number is. So the L numbers, possible L numbers for this one would be 0, 1, and 2. Okay, just start from 0 and go up to this number. If we were talking about n equals 3, then you could go as high as 3. And you could have these different shapes. Okay? The next one is the magnetic quantum number. The magnetic, or M sub L, is based upon one of these. And it goes from possible, let's take this one. It goes from negative that number, stepping up in increments, whole number increments, to positive that number. So it would be -2, -1, 0, +1, +2. Those are the possible orientations in space of those L orbitals, right? The orbitals of that shape could be directioned in these either one of these 5 different directions. And the last one is really simple. M sub s is the electron spin quantum number. It can be plus 1/2 or minus 1/2. That's it. So any one of these could have a plus 1/2 or a minus 1/2 spin. Just pick one. It doesn't matter. That one. Okay? So that's why I say they're nested. This is derived from one. That's derived from one of these. These are derived from one of those. Right? If you have 4 here, then you could have a possibility of 0, 1, 2, 3, or 4. Now, why do we need all these? Well, it's probability functions, but this tells us how many electrons that we can have in various positions around an atom. Right? If you only have one atom, one proton and one electron for hydrogen, then you can only have this one, that one, and one of these. Right? That's it. Only one electron. Right? So this one is restricted to that. Well, this or that. And then subdivide there. But if you only have one electron, then you only need this one, right? It's the lowest energy. All right, so now that we have all those numbers spinning around in our brains, let's see what we can do with them. This table can be confusing, but if you take it logically, here's your n's, 1, 2, 3, and 4. Here's the L's that are possible, right? If you have n equals 1, you only have one possible L. I'm sorry, that's not right. If you have this one, that's the only possible one. Right? And then the magnetic quantum number can only be 0. Right? Because -0 is 0. And then the number of orbitals, you can only have 1. What do we mean by the number of orbitals? That is, we sum up all the possible combinations. Okay. Now we have, if we try to write the electronic structure of an atom, right? Position every electron in its place in a structure. If you just use numbers, that can get very confusing and open you up to mistakes. So what we do is we keep these as numbers and we assign letters to these. So the 0 is an S. The 1 is a P. The 2 is a D. The 3, SPD, F. And the 4 is a G. And you can go on up. But that covers pretty much everything in the periodic table. That's why 1s, the 1 and the 0 combined is 1s because 0 is s. And this one could be 2p. If it's 0, it's 2s, and if it's 1, it's 2p. If you go to 3, then you've got 0, 1, and 2. You know, I think I made a mistake before. If you have 3 here, you can only go 0, 1, and 2. I hope I expressed it that way. If you have 4 there, then you can go 0, 1, 2, 3. The only way you can get to 4 is if you have 5. Then you could have 0, 1, 2, 3, 4. 1, 2, 3, 4, 5. Right? You're going to have 5 L's for that number, starting with 0. I just wanted to make that clear. It's confusing enough as it is without your instructor making mistakes. Okay, so now that we know how to write these orbitals, we need some rules to tell us how do electrons go into those orbitals as we increase the number of protons and electrons, that is, we work our way through the periodic table, right? We go from very simple, get more complicated, more protons and electrons. How do they go into those orbitals as we build? All right, for n equals 3, we're allowed 3 subshells, which is L's. Right? That's simple. And for each L, you could have let's see. For L equals 0, right, we're starting here. So we can have these. So for L equals 0, you can only have 1 m/ml. For this one, you could have a 3p for L equals 1 and a 3d for L equals 2. But within each one of these, you can have further sublevels. Okay, so we need to look at those also. Suppose we have an L equals 2. All right, we come down here, got a 2. Right? How many magnetic quantum numbers do you have? Well, you have this list right here. Okay. So that's number of orbitals that are assigned to the D could have 5 orbitals, right? And while we're here, each one of these can have 2 electrons, one with a half spin and one with a plus and one with a minus half. So that means you can have 2, 4, 6, 8, 10. 10 electrons can be positioned in that L orbital, L equals 2. All right, so this is a way of looking at shapes. I'm going to breeze through these because they're very complicated, right? So the distribution here is spherical for all these s orbitals. But notice as you get higher, you have, if you go from 1s to 2s, you actually have a node in there. A node is a region of space in an orbital where you predict 0 electron density. Right? So that's what it looks like in a picture. This is what it looks like on a graph, where you have 0 density right there. For 3, you have 2 places, 2 nodes right there and there. Okay, I'll just leave that as is, and we'll, if we need to, we'll come back to it. All right, this is the shape of a P, right? Remember, L describes the shape, and the p orbitals are dumbbell shaped like that. See? Now we can have 3 of them, right? If you have p equals 1, you can have a -1, 0, and a +1, right? So they're dumbbell shaped. This one points in one direction, say the x-axis. This one's the z-axis, and that's the y-axis. Okay, so that's the way they point. Their orientation in space is the magnetic quantum number. All right, D's get more complicated, right? So there's a -2 probably, and then a -1, and then a 0, and then a +1, and then a +2. Well, I don't know if that's right, but there are 5 of them, and they have all those different shapes, and they're pointed in different directions. And the F gets even more ridiculous. Well, these are D's, excuse me, these are D's, and the F's are even worse. And the D's can have 7, right? Because F's, excuse me, the F's can have 7 because you can go -3, -2, -1, 0, that's 4, 5, 6, 7. And put 2 electrons in each, you have 14 electrons. Okay, so our rules. The Pauli exclusion principle simply says, in a given atom, no 2 electrons can have the same set of 4 quantum numbers. what would happen if they did? If they did, you would be trying to put two electrons in exactly the same space and shape and everything, and just try to put two negative charges together. They won't do it. So Pauli exclusion says you got to have a unique set of 4 numbers for every electron. That may only be a change in spin. Maybe that's all you need. Just change that last number. Okay. The problem is we cannot calculate electron repulsions because we don't know where they are. So we have to work in terms of probabilities. And when electrons are placed into the atom one at a time as you add protons, of course, then they go into a particular order. And the problem is that when you get more than one electron in there, you don't, that order tends to change. Sometimes it flips the more electrons you get. So you might expect an energy level 2 of a certain type to be at this energy, and then the 3 would be above it. But in some cases, you'll end up with the 3 being higher than, being less than the p orbital. Now this doesn't show us exactly how that happens. I think the idea here is that you expect everything with a 2 to be the same energy level, right? This 2p should be at the same energy as 2s. But that's not the way it happens. When you start getting electron interactions, that pushes the p up a little higher in energy. Right? So in general, 2s are similar energy, but they can vary. All right. I've got 15 minutes left. Let me see if I can reach a good stopping point so I can come back and finish this video later. Let's see. Penetration effect. All right, what do we mean by the penetration effect? The penetration effect occurs as you accumulate more protons and electrons. Right? So you would see a penetration effect as you go to higher numbers of protons, as you increase and get new elements, different elements. What we see is that the effect of the p orbital electrons, the s orbital electrons, has a greater density close to the nucleus than the 2p does. That is, the 2s orbital penetrates toward the nucleus. That's where that term comes from. What is that? What is the ultimate effect of that? Well, it causes an electron that's located in that 2s orbital to be attracted more strongly than an electron in the 2p orbital, right? And stronger attraction means lower energy. That's why that 2p was at a lower energy level. The 2s was at a lower energy level than the 2p because of penetration. The probability puts the electron more often close to the nucleus. It penetrates toward the nucleus. So this is what it looks like. Right? For a 2s, remember, you're going to have a node, right? It's not 1s, it's 2s. So the 2s has one node here. But it also has more electron density closer to the nucleus than the p does. You may have significant amount of probability for s out here, but this penetration offsets that and gives you lower energy for the 2s than the 2p. Okay, similar things happen with the 3s. It has 2 nodes, but it penetrates these 2 levels here, penetrate toward the nucleus, more so than a p orbital would. Now when you combine them, you see that the s penetrates deeply, The P penetrates a little bit also, more so than the D. So that gives us an energy level. S is lower energy, P is the next, and D is higher. Okay, this would be a good place. This would be a good place to stop, where we're just starting to talk about the periodic table, because I want uninterrupted discussion of the periodic table, because the structure of the atom is why the periodic table is built the way it is. Okay, and I want to draw that comparison in one meeting. The periodic table is arranged in a pattern that takes advantage of what we know about the structure of the atom. But the periodic table wasn't always that way. In fact, it developed over several decades, first based upon trends. The Johann Dobereiner recognized that there were triads of elements, which means 3 elements, that shared similar characteristics. One of the most notable is the halogens, chlorine, bromine, and iodine. They have similar behavior in a chemical reaction. They have similar, some similar physical properties. There were other triads, 3-element groups, but Dobereiner didn't take it any further than that. He just observed. Then there was a German, Julius Meyer, who recognized a more expansive relationship of properties and chemical behaviors of the elements. And he arranged some of the elements in a table of sorts. But it wasn't until Mendeleev came along, and Mendeleev not only saw the relationships among the elements and put them in families or groups, but he also used what he knew about the physical and chemical properties of the elements in these groups and the relationship of one group to the other. He used that information to make predictions about missing elements. At this time, the only thing that was known about elements in a quantitative fashion was mass. They knew that this element weighed more than this element, and they knew the ratio of those weights. They didn't know about protons and neutrons and electrons. They didn't know atomic numbers. So Dmitry Mendeleev was able, with that knowledge and the knowledge of not just the mass of the elements, but their physical and chemical characteristics, that he arranged them in groups, and he saw that there were spots in the table where there were missing elements. That if his trends were correct, then there should be an element in that spot. And he didn't just let it go at that. He predicted the mass of the element relative to the other elements and its chemical and physical characteristics, such as density, reactivity with other elements, that type of thing. And he said, one of these days, you're going to find an element and it's going to fit in that hole, and it's going to have these characteristics. That's why Mendeleev is given credit for producing the first useful periodic table, because of its predictive nature. Now, the first Mendeleev periodic table was not arranged. Groups now are up and down. Mendeleev's first table was groups left to right. But the second publication of his table made the 90-degree shift and put the groups in verticals. Okay, so a little more about the structure of the atom, and this is going to help us segue into the periodic table and its structure. And that is what's called the Aufbau Principle. Aufbau is a German word. I don't even know what it means, literally. But the best way to think of the Aufbau Principle is do it this way. In other words, put the elements together in order, adding electrons in order in a certain way. And that certain way is that as you add electrons and you build elements, bigger, larger and larger elements with more protons and more electrons, the electrons go in at the next highest energy level. In other words, you want the lowest possible energy for every electron in that atom. So if the lower energy levels are already occupied, you go to the very next highest energy level. So oxygen here is one example, right? The lower energy levels are going to be number 1 for the principal quantum number. Then you go to number 2, principal quantum number, and the S is going to come before the P. So when we write these, there's oxygen. Let's pick a different one. Let's go next door to nitrogen. So nitrogen, the neutral nitrogen atom has 7 protons and 7 electrons. Okay, so with 7 electrons, you put them in, and each of these orbitals, the suborbitals, can only have 2 electrons. Right? So the S's, since the S's only have 1 magnetic quantum number, right, the S orbital only has a 0 magnetic quantum number, then it can only have 2 electrons. So there they are, 2 electrons. Now we have 5 more electrons that need to be put in there. So we go to the next level. And the next highest energy level is the 2s. It can only have 2 electrons. Now we have 4, and there are only 3 electrons left. But with 2 as your principal quantum number, remember you can have a 0 and a 1 as your L. Or you can have S and P is the letter equivalent. So next you would go to 2P. But P can have 3 sublevels, -1, 0, +1. Sometimes we designate it X, Y, and Z. So if we had X, Y, and Z, 2Ps, 2Px, 2Py, 2Pz, each one of those can have 2 electrons. So you would have 2 here. Well, actually, you'd fill it up like this. You would say, you would have 1 plus 1/2. We call it spin up. Then you would have the next one, plus 1/2, spin up. And then you would have the next one. So that's 3. 1, 2, 3, 4, 5, 6, 7. 7 electrons. Sometimes instead of writing it like that, we just put all 3 of them into the superscript of the P. Now, there's a certain way to fill these up. And in the beginning, it is logical, right? The 1s come first, then the 2s, then the 3s. Once you get up past the 3s into the 4s, then things start to get dicey. And there's a method for knowing which one comes first, because sometimes the 4s come before the 3s. And it's all because energy. The lower energies in this format are to the left. Okay. Another rule, Hund's rule. And I just actually showed you Hund's rule, I just didn't name it. this one has 3 suborbitals in the p, right? X, Y, and Z. We have 3 electrons that need to go into the p orbital. Hund's rule says that you cannot pair up any of those electrons until each one of the suborbitals has 1 electron. So this one has to have 1. You can't pair it up. You have to go to the next one and the next one. And we're all out. If this were oxygen, you would have 8, right? So we would need 1 more. Now that you've got all of them with 1 in each one, then you can go back and start pairing them up like that. Spin up, spin down. It actually makes sense, because if you put 1 in here and you try to put another one in there, they're both negative charges, right? They repel one another. And that would elevate the energy level too high. So to keep the energy level down, you put them in unpaired first. And only when you are forced, start pairing them up. That is Hund's rule. So we've got the Pauli exclusion principle, we got the Aufbau principle, we got Hund's rule. Those all have to be obeyed in constructing our atom. There's oxygen, and the authors like to use these boxes with a double barbed arrow on them. That's too much time and too much trouble. I use a line, simple line, and a half barb arrow to show up and down. It's quicker, easier that way. Okay, this is what's known as the orbital diagram, or the electronic configuration of the atom. Now, a word about valence electrons. What is a valence electron? Well, a valence electron is anyone that occupies the highest energy level based on the principal quantum number. Right? So all the electrons that have the same principal quantum number are counted as valence electrons. So we'd have 2 here and 3 there. Nitrogen has 5 valence electrons. And notice from the periodic table, if you work your way from left to right, count across 1, 2, 3, 4, 5. Nitrogen is 5th from the left. It has 5 valence electrons. And in the old system of numbering groups, nitrogen is in the 5A group, Roman numeral 5A. It has 5 valence electrons. Okay, so for oxygen, we'd have another one here, right? So that would be 6 valence electrons for oxygen. Okay. Now, the way that the periodic table is arranged can be subdivided or grouped into orbital filling areas. The first 2 groups, the alkaline metals, the alkaline earths, you're filling s orbitals. Always. Always filling an s orbital. And the principal quantum number is equal to the period number. Right? So the period number is 1 here, 1s, 2, 2s, 3, 3s, 4, 4s. Just like that. Simple. Then, on the other side of the periodic table, you get into this group of 6 elements, 1, 2, 3, 4, 5, 6 in that row. Right? P orbitals have 3 suborbitals with 2 electrons each. That's 6 electrons. So 1, 2, 3, 4, 5, 6. When you get to the noble gases, the p orbital is full. Right? That's why noble gases don't react. They're happy. All their orbitals are completely filled with electrons. there's no need to get electrons from anywhere or donate electrons to anybody. All right. So this is the P group. This is the S group, and with helium, of course. Helium only has an S. And then in the middle here, the transition elements, those are all filling d orbitals. And we'll show you that in just a few minutes. Notice that here, so let's take the third period. 3s, third period. 3p, third period. But when you get down here to 4s, and you get into the transition elements, you have to back down to 3ds, right? Because at the third level, n equals 3, you can have 0, 1, and 2 L's. Well, this is your S's, that's your P's, and that's your D's, right? So the D's can have m sub L equal to -2, -1, 0, +1, +2. 1, 2, 3, 4, 5, and then each one of those can have a +1/2 or a -1/2 electrons. So 2 electrons for each one of those means 10 electrons filling the d orbitals, right? And I'm going to show you in a minute how you know which one comes first. You fill the d orbitals, look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When you get to this far right side, in this period, fourth period would be zinc. You would have 10 electrons in that d orbital. And then when you add the next electron to go to gallium, you put it in the 4p. Okay, and this is all based upon energy levels. At this point, 4s is lower energy than 3d, probably because of penetration. The 4s penetrates deeper than 3d, which means that the electron density is shifted enough toward the nucleus to lower its overall energy. Okay. So once you get that 3D filled, you can go back to the 4Ps. Notice that the S's and the P's are all corresponding to the period number. Right? That's all the way down. The D's back up one N number when you get into the crossing that period. Now when you get to the lanthanides and the actinides, you're filling F orbitals. And they're stuck right in here in this sliver. When that happens, you back down not 1, but 2 N numbers to get the Fs. So for this 6, that lanthanide group is going to be 4F, not 5F, 4F. In fact, 5F doesn't come until you get to the actinides. The lanthanides are 4F, the actinides are 5F. Okay, so that's the structure of the periodic table. And if you recognize that structure and how to read the table, you can write the electronic configuration just looking at the table. You can tell how to write the electronic configuration from the table. But I'm going to show you how to do it the hard way first, and then we'll come back to the periodic table to do it the easy way. All right, so how do you know that 3D comes before 4P, 4S, 3D, 4P in that fourth period? Well, this is one way. You write all the S's down here, 1S, 2S, 3S, 4S, just put them all down there. And then next, you can have a P for the 2S, so you write the 2 P's, 3P, 4P, 5P, 6P, 7P. Just do that. Then 3 D's, still on the 3 line, 3, 4, 5, 6. That's all you're going to need anyway. Then 4F and 5F, because That's the lanthanides, and this is the actinides, and there's nothing past that. So you might as well stop. Okay, now to tell the order, you do the diagonal, right? You go from upper left, right to lower left here in each group. There's only one of them, so it's just in that square. There's only one here, and then you go over here and you take it diagonal there, 2p to 3s. Then you have to turn around and go back out here. 3p, next neighbor over, start up in the upper right-hand corner, 3p, 4s. Then you go over here, which you haven't done this one yet. Then you go diagonal there, 3d, 4p, 5s. And then 4d, 5p, 6s. So that diagonal approach gives you the proper order in energy of each of the orbitals. Okay, so let's take an example. 3 examples, actually. We'll do sulfur first. Right, where's sulfur? Well, let's look it up. Right. Sulfur is right here, under oxygen. Right, it has 16 protons, which means 16 electrons for the neutral atom. Okay, so we just start filling them in. 1s, 2s, 2p, 3s, 3p. If we need more, we'll add them. So there's 2 more, 6 maximum for the p's, 2 more for the s's. So let's see how many we got. There's 2, 4, 6 is 10, 12. We got 4 more. So all of those 4 electrons can go into that p orbital. But just to check your Hund's rule, right? You got X, Y, and Z. So you put them in 1, 2, 3, 4. Does that look like anything you've seen before? Oxygen. It's in the same family as oxygen. Only now, instead of filling the 2p for oxygen, we're filling the 3p for sulfur. And it has the same arrangement of electrons in that orbital. It has the same number of valence electrons too. Oxygen would be, well, oxygen would be 2 and 4 would be 6. But sulfur has 2 and 4 and 6 valence electrons also in the 3rd energy level. Now, another way to write this, shorthand. Notice that that one's full, that one's full, that one's full. And then we start a new energy level here. So which one would be that one? If we only had this many, here to here, which element would that be? Well, to find out, you just start at sulfur and you work your way backwards. You go back, 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 and then you have to wrap up around. Neon. Neon has 10 electrons. Right? 10 electrons. And then add the extra for sulfur. Right? That's a shorthand way of writing. You don't have to put that 10 in there. You can if you want. That's a shorthand way of writing sulfur. Now, for something like sulfur, which has, you know, a short list, it's not a great advantage. But when you get something big, lots of electrons, it can come in handy. Like for barium, right? Where's barium? Barium is an alkaline earth metal, and it's in the 6th period, way, way down here. 56 electrons. So we're going to start over here, way over here. Barium, 56. Okay? Now, here's where we need that diagonal chart to tell us what to do next. And I've got my hard copy here, so I can use it. Yeah, right here. See? That former slide. Okay, so if we don't look at the periodic table, I could do it by looking at the table, but if I look at the diagonal, then I do it this way. We'd have 1s. I'm going to start putting electrons in as I go. 1s2, 2s2, 2p6, 3s2, 3p6, 3p6, okay. Then 4s2, and then 3d10, and then 4p6. Let's see how many electrons I've got. 2 plus 2 is 4, and 6 is 10. And 6 and 4 is another 10, so that's 20, 30, 36. I got 20 electrons to go. So 4p followed by 5s, and then followed by 4d. So that's 12. 8 more electrons. So I'm going to have to wrap around. So I got 4d, then 5p, right? We got a 5s, now we need a 5p. 6, and then we get the 6s2. So let's see if we got all our electrons in here. There's 2, 4, 10, 2, 4, 10, 20, 30, 40, 8, 50, 6. Okay, so that's the electronic configuration for barium if you write it out, the entire thing. Now we use the shorthand, right? So you look at your periodic table and you say, okay, here's barium, right there. Let's back up until we find a noble gas. Barium, cesium, 6, then we have to move up to 5. Xenon, 54. Xenon. (54) from 56 leaves 2 electrons. And then we only need this one. That's the shorthand version of barium. Now, you're probably wondering, how do I answer that type of question on a test? Well, if the test question asks you for shorthand electronic configuration, you can use this. But if it says, write the electronic configuration of element such and such, do the whole thing, all of it. Okay, so there's the shorthand. How about europium? Well, let's see. We've got to find europium first. So let's look at our periodic table and see if we can find europium. Let me see. I'm thinking it's down in the, it's either a lanthanide or an actinide. There it is right there. EU is 63. All right. Okay. So what do we do with EU? Right? Well, we're filling F orbital. Let's use the periodic table to our advantage this time. All right. Let's just write the shorthand for europium. Save us a lot of time. If you're backing up to find a noble gas, where do you back to? Well, you go back here, but then you have to go up here to the lanthanum, right? Because that's a lanthanide. And then you back up past barium, cesium, to xenon 54. Xenon 54 is the nearest noble gas. Okay, so how many does that leave us? 9, right? 54 is 9 electrons. All right, how do you put them in there? Well, you go from xenon, and then you start walking your way toward europium. All right, here's xenon, and you're wrapping back around here. So what do you have here? S orbitals. 6s is being filled there until you get to barium. All right, 6s2. All right, once you get past barium, what do you have? Lanthanum. Right? This is 6. Lanthanum is a 5d because you're in transition metals. All right, so you have a 5d1. And then you go down because these elements right here are actually squeezed into that crack between lanthanum and hafnium. Right? So you say, which f orbital is this? Well, if that's a 6s and this is a 5d, that must be a 4f. Now count how many electrons. Start with cerium. 1, 2, 3, 4, 5, 6. Okay. Now let's see if we got all our electrons there. Let's see, 54, 55, 56, 57. 57 and 6 is 63. Yep, that's it. That should be the correct electronic configuration. What happened? What happened to 5D? Okay, that's wrong. There should be a 5D in there. Hold on, I can make that correction. Where is 5D? 5D1. Okay, and some periodic tables, that one doesn't have it. Some periodic tables actually have a partial electronic configuration built in to each one of the squares. Or you can look it up. In fact, I think I will. On my other computer. So I'm going to say europium. Electronic configuration. All right. Europium, here we go. All right. Oh, 5D0. Okay, this is one of those screwballs. 5D is empty. Okay, here's what's happened. All right, I'm just going to tell you right now. This is what you would expect, right? If you follow the Aufbau Principle. Except that Hund's rule, well, not a Hund's rule. The Aufbau Principle, yeah, that's the right one. The energy level for F tends to be a better or a lower energy than 5D with that electron in there by itself. Why? Because the F orbitals have 7 possible suborbitals. Okay? If we only put 6 in there, 3, 4, 5, 6, they're not happy. They're really kind of screaming for another one. Half-filled levels and whole-full levels are preferable. So when you get yourself in this situation, what happens is that electron moves over there. And that's why the d orbital is empty. So this is really, that's true. It's just there was no explanation given for it. Right? There's no way for you to know that unless you're told. But it's funny that way. And this happens in several places in the periodic table. Half-filled, if you're within one electron of a half-filled level, it will steal the next lowest electron and put it in there to fill it up. We'll encounter those again later. Maybe not today, but during the review, perhaps. All right. So that takes some practice, writing these electronic configurations. And there are several of them in the review document. So I encourage you to go in there and practice. Or just go into the periodic table and pick one and write the electronic configuration. Now, while we're on the topic, what would you do if you had an ion formed? Say, oxygen tends to be 2-, correct? We already know that. Oxygen, 2-. So oxygen has 8 protons and normally 8 electrons. But a 2- adds 2 more, so it has 8 electrons, correct? So what would that be? 1s2, 2s2, 2p6. Oop, too many. No, I said that wrong. 8 plus 2 is 10. I can't even count. So that is 6, 7, 8, 9, 10. Okay? That's how you would write the ion. You count up all the electrons. Neutral plus the extras. Or if it's a positive ion, neutral minus the ones you lost. Now, what's funny about this? 1s2, 2s2, 2p6 is the same electronic configuration as neon. Interesting, huh? That's why oxygen wants to gain those 2 electrons. Makes it look like neon. Gives it full orbitals. They love full orbitals. So that's one of the driving forces of chemical reactions, to complete orbitals. Okay, we'll talk more about this later. I just thought the opportunity presented itself, and, you know, since we're on the topic, I just introduced that subject. Okay, so we can use the periodic table to write electronic configurations because we know how it's arranged with S fillings, D fillings, P fillings, F fillings. We don't need that diagonal chart. We just need the periodic table, and we have to understand some of those quirky things that are in there. Okay, there are other things that you can do with the periodic table. You can see trends, properties of the atoms. And these are the 3 ones that we're going to look at today. Ionization energy, and I'll define it in a second. Electron affinity, and atomic radius, which means how big is it? Okay, ionization energy is defined as 1 atom or 1 mole of atoms in the gaseous state, and it loses 1 electron. Still in the gaseous state, and it lost an electron. That's it. Now, why do we put it in the gaseous state? Like a metal or a liquid. Why do you want to put it in the gaseous state? Simple. How do you get that electron to go? You have to add energy, don't you? Right? You have to add some energy to kick that electron out. Now, we're not talking about light now. We're just talking about, you can do it by heat. Just raise the temperature. Add the energy. and pop that electron out, it goes to infinity. Well, if X is a liquid or X is a solid, it takes a lot of that energy for a physical phase change from solid to liquid, liquid to gas. We don't want to know that. We want to know how much energy it takes to pop that electron out. That's all we want to know. So that's why X has to be a gas, regardless of how it starts under standard temperature and pressure. We need a gas here. And then we make that one. Now, this is the ionization energy. In fact, this is the first ionization energy. Okay, I need a fresh marker. This is I and E, ionization energy 1, first ionization energy. That's the amount of energy it takes to remove an electron from a neutral gaseous atom. Okay, you can take this one, you know, if there's some more electrons in there, and you can pop another one out. That's the second ionization energy. And if you got more electrons, you can keep going. Second, third, fourth. Okay, but this is the first ionization energy. Magnesium is our example here. First ionization energy is this much, 735 kilojoules per mole of magnesium gaseous atoms. Notice that when you go for the second ionization energy, it takes more, right? Well, for one thing, the second electron is coming from a lower energy state. But not actually, right? It's coming, magnesium has 2 s electrons, so they're coming from the same energy level. So we need another explanation. The explanation is you're trying to remove a negative charge from an already positive charge ion. And that takes more energy, right? Try to remove a negative from a positive that's attracting it. So it takes twice as much energy to kick off the second electron. Now, magnesium, at this point, right, here's magnesium. If you kick off one electron, what electronic configuration do you have? It looks like sodium now, the neutral sodium atom. But if you kick off a second one, what does it look like? Now it looks like neon, and it's very happy. So if you want to remove an electron from magnesium when it looks like neon, it's going to take a huge amount of energy, right? Because you're removing it from a happy atom. Magnesium is fairly willing to give up 1 electron, even 2 electrons. But once you get down to what we call the core electrons, these are valence electrons. Magnesium has 2 of them. The valence electrons are relatively easy to remove. The core electrons are very tenacious. They don't leave without extra prodding. Okay, so that's ionization energy. Now, how does ionization energy, the first ionization energy, trend in the periodic table? Okay, that's what we're going to look at next. If you go across a period from left to right, the first ionization energy increases. All right, here's the explanation. As you go from left to right, all the electrons are in the same energy level, right? For instance, the second period, n equals 2. But you're adding protons to the nucleus. So you're increasing the nuclear charge while you're not increasing the energy level of the electrons significantly. So that means there's a stronger positive charge pulling on those electrons, which makes it more difficult as you move to the right to remove those electrons. Okay? Now, that was period. How about groups? Go up and down in a group. Well, if you go from top to bottom in a group, what's happening? Well, you are adding protons, right, as you go down, and you're adding electrons in higher energy levels. But those higher energy level electrons are much easier to remove because they're closer to infinity. Plus, the electrons that are below them, the core electrons, are shielding some of that positive charge from the nucleus. So they don't feel the positive charge as much out on the outer reaches of the electron clouds. So as you go down, the ionization energy decreases. Conversely, if you go up in a period, the ionization energy increases. So put those both together. Increasing what? Up and to the right. So from lower left to upper right, you get an increase in first ionization energy. Okay, that's the trend for ionization energy in the periodic table. This is a diagram that shows it's going in order of atomic number: helium, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And you can see for these first 6 periods that the highest ionization energies are located where? With the noble gases, right across the top there. But as you go down the group, right, the energy becomes less and less. So that follows the trend that we've just predicted. So then when you move from helium to lithium, you're into a higher s orbital, period 2. So that electron takes much less energy. It's a valence electron. As a general rule, valence electrons take a lot less energy to remove than core electrons. That trend holds fairly well. So we add another proton to beryllium. We're moving across lithium, beryllium, and we get an increase in energy. Now, why does it dip down here for boron? Well, notice where boron is. Boron is in the second period, but now you're removing p orbitals, and they're at higher energy level, so it takes less energy. Right? So you get that discrepancy there. So that valence electron is easier to remove than the second s orbital electron from beryllium. And then you get a similar jink from nitrogen to oxygen. But this one's for a different reason. Okay, let's draw our configuration for nitrogen and oxygen. So there's 7, there's 8. We have 1s2, 2s2, 2p4, 3, 2p3, 3, 4, 5, 6, 7. 1, 2, 3. There, there, there. Okay? For oxygen, you got 1s2, 2s2, 2p4, which means they're going to be like this, 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 and that. Okay. When you're removing an electron from nitrogen, you have to take it from here. Right? So it follows the trend. It's to the right of carbon, so it's going to take a little bit more energy, right? Carbon's there, nitrogen's there. But when you get to oxygen, you've got these paired electrons. They're repelling each other. They're in the same suborbital, and they're repelling each other, which makes it easier to remove one of them. And that's the one that gets kicked off, first ionization. And it takes less energy than one of these would. So that's why oxygen jinks back down like that. You'll see the same thing, phosphorus, sulfur. You don't quite see the same thing over here with arsenic and selenium. Right? They show arsenic, but selenium's here. They're almost equal. And the reason for that is by the time you get down there, the energy level's way out here. There's not a whole lot of difference between them. But for these lower energy levels, that holds true. Okay. So, this slide is a takeoff on that description that I just gave you. Why the graph of ionization energy versus atomic number across a row is not linear. In other words, you have those jinks, a couple of jinks there. And they're one of two different reasons. Right? The one that I just described was electron repulsion. And that could be construed for boron and aluminum, but it's more likely that the difference is the fact that, let's see, let's go back. There, boron and aluminum, see, they jink down. That's because you're removing an electron from a p orbital rather than an s orbital. Remember, the s orbitals have some penetration toward the nucleus, so they're more strongly held than the p orbitals. So the repulsion idea doesn't work for them, but it does work for those places. Beryllium to boron, okay. You do get that change for beryllium to boron, but I don't think it's entirely electron repulsion. I think it has to do more with the energy level. Nitrogen oxide, yes, that's electron repulsion. Okay. Which one of these would require more energy to remove an electron? Sodium or chlorine? Look at your periodic table. Where are they located? And these are neutral atoms. Sodium is in the same period as chlorine, but it's way to the left. That's the lower energy side. Chlorine is to the higher energy side, right? So chlorine takes more energy to remove an electron. Okay, how about lithium and cesium? Now we're in alkali metals. Lithium is at the top, cesium's at the bottom. The trend there is the top takes more energy than the bottom. So more energy is required for lithium to remove an electron. First ionization energy. Let's talk about second ionization energy, which has the larger second ionization energy. So let's use our electronic structure to answer that question. Lithium has 3 electrons. Right? 1s2, 2s1. Beryllium has 4. 1s2, 2s2. Okay? Now, first ionization energy does what? It removes one of these, right? So now, that one has a 1s2, and that's it. The 2s1 is gone. Beryllium, after we remove one electron, now we're going for the second one. 1s2, 2s1. Now for the second ionization energy, we have to remove that electron for beryllium or that electron for lithium. That's a core electron, not a valence. This is a valence electron. So it takes more energy to remove that electron than it does to remove that electron. Okay? This is a table out of your book, and it just shows the first, second, third, fourth successive ionization energies for each of the elements. Now, why does sodium stop at 2? Well, doesn't have to. Could go higher. But what are we trying to show? We're trying to show the difference between valence electron ionizations and core electrons. So sodium, you only need to remove 1, and now you're into the core for the second one, just like lithium. Magnesium, you remove 2 before you get to the core. Aluminum, remove 3, get to the core, so on and so forth. Okay. Next trend, electron affinity. Electron affinity could easily be mistaken for the reverse of ionization energy, but it's not. Why? Because for ionization energy, we're starting with that, and for electron affinity, we're starting with that. But instead of removing an electron, we're adding an electron. And for the same reason, it's all gases. We don't want any influence from phase changes. So the ionization energy is going to be a positive number. You have to add energy to the system to get the electron to kick off. This one, when you add an electron, you're going to get a negative value for energy. Right? This one's going to be energy on that side. Right? So you get some energy out of this one. All right. So that value is going to be written separately. It would be a negative number because energy is leaving the system. As you add an electron, you get some energy out, so it's going to be a negative, right? And the stronger the electron affinity of that element, the more negative that number. That's important to recognize. The higher the negative number, the stronger the affinity. Now, what happens when you go across the period from left to right? The affinities become more negative, which means the attraction is stronger. Okay? That's what that means. Now, why does that happen? For the same reason the ionization energy happens. When you move from left to right, you're adding more protons, but you're in the same energy level. So you've got more effective nuclear charge attracting electrons. So if you go from lithium across to fluorine, fluorine is going to have the most negative delta H, or the strongest electron affinity. Okay? Now, what if you go down a group? Down a group, you're adding to outer energy levels. Right? So the nuclear charge, for the same reason as ionization energy, the nuclear charge is being shielded by those inner core electrons. So any approaching electron that we might want to add doesn't feel as strong a charge pulling it. So as you go down, the electron affinity becomes less, or the value becomes less negative or more positive. Okay? All right. So what's the trend for electron affinity? It's the same as ionization energy, except the numbers are reverse signs. So as you go from lower left to upper right, the strength of attraction for electrons for the neutral atom is stronger. The electron affinity increases or becomes more negative. That means when it happens, you get more energy out. Okay, that's electron affinity. How about atomic radius? Well, what's happening when you go across a period? You're adding more protons, correct? But they're in the same energy level. So you're getting a larger effective nuclear charge that's pulling on those electrons. And what it does is it shrinks the size of the orbitals, which means the radius decreases as you go from left to right. How about go down in a group? What's happening? Well, you're adding protons, and the inner electrons are shielding them, but you're also adding electrons to the next outer energy level. So that makes the atom get bigger. So as you go down, the atomic radius increases. Vice versa. If you go up a period, up a group, the radius decreases. Okay, so put those two together, and as you go from lower left to upper right, the atomic radius decreases. And this is a general trend, right? It works fairly well for what we call the representative elements, those that fill s orbitals and p orbitals, right? From here to there. That trend works fairly well. It gets kind of wishy-washy in the transition metals. Okay, those are the three most important trends in the periodic table. They're the ones that we're going to discuss now. There are others, but these are the more important ones. And notice with this discussion of atomic radius, what they've done. They left out the transition metals altogether, because the trend works better when you stay with the representative elements, the s orbital filling, the p orbital filling. All right. Okay, which one of these should be larger, sodium or chlorine? Well, left to right, pardon me. All right. Which should be larger? Remember the trend. Sodium and chlorine are in the same period. So as you go from left to right, the atom shrinks, right? The neutral sodium atom is bigger than the neutral chlorine atom. Okay, how about this trend? Lithium and cesium, all right? They're in the same group. Lithium's high, cesium's low. So cesium should be larger than lithium, because we're adding electrons to outer orbitals. Just makes it bigger. Now, we're not saying anything about ions here. Right? You can discuss ions in those terms. But in general, if I make an ion out of one of these atoms, what is its radius going to do? It's going to shrink, right? You remove an electron, right? That space is now empty, right? So ions tend to shrink compared to their neutral atoms. Or if you add an electron, like chloride, is going to be bigger than the neutral chlorine, because you're adding an electron to the outer shell, and that balloons. Okay. Now let's see if we can say something about the orbital itself. the space that's occupied by the electrons. Let's see, be sure I'm still on. There we go. All right, how about hydrogen 1s orbital and lithium 1s orbital? Hydrogen looks like this, and lithium has this, 1s, 2, 1, like that. Now let's just focus on the s orbital itself, not the electrons that are in it. Although, you know, they do have an impact, but if we're just looking at the size of the orbital, what influences that size? Well, since they are close to one another, and since we're looking at only at this one right here, what affects the size of the orbital? Well, if it has electrons in it, the attraction to the nucleus is going to cause the orbital to either shrink or balloon. Right? You've got 3 protons here, and this is right close to the nucleus, both of them. 1 proton there, this one's going to be bigger than that one, right? So even though we're saying this is an energy level 1 and that's an energy level 1, and it's an S and an S, the reality is that this S sits closer to the nucleus, which means what? It's lower energy. Closer to the nucleus means lower energy. Right? So that's the larger one. But this one's closer to the nucleus, it's lower energy. All right? I know. It's like learning any new language. There are rules, grammar, and syntax rules that you learn when you learn a language, typically, if you learn it in school. I mean, if you're immersed in the language, you just absorb it. But if you learn the rules, and then you start speaking the language with someone who's a native speaker, say, wait a minute, that's breaking the rules. They say something. Well, no, not really. The language is the language. The rules were written just to try to stabilize the language. So the rules here say that 1s is the same, 1s is equal to 1s. But in fact, depending on the atom that it's attached to, the 1s is slightly different. And that's the same trend for any of the orbitals. That's why it's so difficult. Well, it was so difficult for Niels Bohr and his model to be able to model anything larger than a hydrogen atom, because things get really complex really fast. So it took quantum mechanics to sort of make sense of it. Okay. So this was supposed to be a video showing you metal atoms in a crystal lattice. And how you determine the distance between nuclei, which would be half the distance between this nucleus and that nucleus would be the radius, correct? Because the distance between those two is, as long as they're touching, the distance there is the diameter. So half of it would be the radius. You can't use these because they're not touching. And there are various methods for determining the radius of atoms, and some work better for some elements than others. So it's sort of a educated guessing game. All right, that would be for solids, metals. This would be for gases. And that's a little more difficult to justify. All right, so we're not going to go into any detail for that. You're just going to have to take them at their word. When a radius is reported, just accept it. And recognize that it's, depending on the author, it could be different for different authors. But they're really close together, and the trends still hold, no matter which author. Okay. Let's see if we can arrange these elements in increasing order of first ionization energy and then atomic size or atomic radius. All right. So let's look at oxygen, fluorine, sulfur. Where are they on the periodic table? Right. Let's see. Let's get a little closer. There's oxygen. There's fluorine to its right, and there's sulfur below it. Okay. So the ionization energy trend is from lower left to upper right. So we're going to go this way. Sulfur, fluorine, sulfur, oxygen, fluorine would be increasing ionization energy. Okay. Atomic size would be exactly the opposite. Right? Isn't that right? Lower left to upper right, decreasing, not increasing. That was easy. Okay. So let's pull everything together. What is it that is the primary driver for the chemistry of an element? It is, in fact, the number and the type of valence electrons. Those are the electrons that are involved in chemical reactions, the valence electrons. The core electrons are just there to fill in space, fill in the lower energy levels. Second, we can derive the electronic configuration, right? 1s, 2s, 2p, so forth. We can derive that from the way the periodic table is organized, because it's logical. S fillings, P fillings, D fillings, and F fillings. Now, one thing we haven't covered yet, unless you did the extra credit for with the periodic table, or you've been working on it, is certain groups have special names. Okay. This first group is alkaline metals. Second group is alkaline earths. The last group is noble gases. The one right next to it is halogens. Now, they're not showing you all of them. The next to the left of that is the oxygen group, or the chalcogens, which is derived from that word, calx. Calx means the combination of a metal and oxygen. So a calx of calcium would be calcium oxide. That's a calx. Anything combined with oxygen. So the oxygen group is chalcogens. The next ones are pnictogens, and starts with a P. The P is silent. P-N-I-C-T-O-G-E-N-S. And I assume that the nicto part refers to nitrogen. That's the nitrogen group. Now, carbon group doesn't have a special name. Boron group doesn't have a special name. Transition metals, yeah, they're all grouped together. And for obvious reasons, you're transitioning from one side to the other side of the periodic table. The lanthanides are a takeoff from lanthanum, right? Lanthanum is right here in this position, and then everything right in that crack is right here. And then this one is the actinium, and everything in that crack is on that level. Lanthanides, actinides. So those are special names that are given to the groups. And those are historical. I mean, they existed, some of them before the periodic table, but others were developed along with the periodic table. Okay. The basic division, metals and nonmetals, right? Where are the metals? They're over here, all the way over until you get to there. right? And if you draw a diagonal line, start to the left of boron and then zigzag between boron and aluminum, and then zigzag again. Only go one element at a time and zag, zig, zag, zig, zag. That separates the metals from the nonmetals. Okay, here we go. So if we draw a zigzag here, right there, and go down and over and down, notice that it's got these blue squares on either side of it right there. These are another special group, and the members of that group vary depending on the author. But they're very close to that border, that line between metals and nonmetals, which means sometimes an element on one side or the other of that line behaves like a metal, and so other times it behaves like a nonmetal. Depends on the reaction environment. Now these are extremely important, these metalloids. They form the backbone of the semiconductor industry. All of your computers, cell phones, all that stuff. They make generous use of those elements. One of those elements is silicon, right here, that first one. Right? Silicon is the substrate for all electronics, all computer chips. Okay, I don't know, this one snuck in there. I'm not going to cover the individual groups and talk about their characteristics. That would just take too much time. We don't have time for it now. It's in your textbook. I mean, if you're interested in one group or the other, you know, there's a whole chapter on there. So just, you know, knock yourself out. Curiosity is your best friend. Okay, so that's it for chapter 7, Atomic Structure and Periodicity. And we'll get together. Let's see, this is Wednesday? Wednesday, yeah. We'll get together next Monday and look at problem solving. All right, so dig into the review document that's in Blackboard. It's got the key there, it's got the work problems, and bring your questions to class on Monday. You can't work too many problems. It's impossible. The more problems you work, the more intuition you will develop about chemistry. So boredom is your friend also, in addition to curiosity. Okay, that's it.